some point in my sleep, I must have like done something to my face because there's just like a little crack.
Yeah, there is.
I don't know where it came from.
I also once there was like crusty blood on it. To be sure, I'm a little concerned.
About what?
Like doing many trials of my code.
So,
Because it
so
takes
is
me-
Patricia.
It takes me, yeah, many ages to do.
But everyone who will read your masterpiece understands that the larger the basis, the longer the simulation. Just address it. Okay.
How long do our presentations have to be?
5 minutes.
Presentations.
5 minutes?
Presentations 5 minutes, but report.
Questions are unlimited.
Can they be longer?
No.
Oh my God.
Okay,
That's crazy.
5 minutes is not that hard.
All right.
So basically.
There will be questions.
Okay, so
You can prepare backup slides, and when someone asks hard question, here are the equations you wanted to see. You can prepare like 12 slides and show only 5, and then or whatever rest will be your backup.
I legitimately have no idea what like equations I'm using. I do, but I don't. I don't know how to like put them in context very well.
Try your best and go.
Try your best. But I don't think that other people watching our thing are gonna be like caring about us trying our best.
They
I'm
want
like,
results.
you say that we try our best, but they're gonna not accept it. I'm like, I did my best, but
I do have options of grading your writing and presentation myself, or give forms to grade to everyone who visits.
you should definitely give your own opinion. I mean, you are the professor.
It's not your own
Not
discretion.
teaching your class.
No.
But my only concern, like, is that Seth is gonna think that I'm, you know,
Too smart.
I know
Seth
his.
can be there.
I don't know.
No, I think he should be impressed because you're doing something really world level competitive.
Are you gonna be impressed with me?
Well, I'm already impressed, but you still can contribute and improve it.
Oh,
Okay, so 4 printed copies of your masterpieces by 11 here in class. If you are not sure if you can print, send it like at midnight to me and I will print. But it's your choice. You want to finish earlier and let me print, or work until last minute and print yourself. Okay?
Okay.
And then each of you will grade 2 works of your colleagues, and then return feedback back to the author, and author will read the feedback and improve for the final iteration due on Monday.
Monday.
Okay,
And so then we just have like 4 days to prepare
right.
our presentations.
Right.
we're gonna do what now?
Monday, final draft is due, and then presentations are due
On Thursday.
Wednesday by midnight.
Yeah.
Right?
And where are we presenting again?
Near the heads of dinosaurs.
Where?
Oh, okay, so
The job.
second,
Yes.
in the lounge?
252. Yeah, 252. And 252. Of Sugi, okay.
Yeah, near the heads of dinosaurs.
Is that the classroom for? Okay, I know where that is.
So, how do we entertain each other during the remaining 38 minutes of the class? So please try to feel this surprise quiz by the end of the meeting, and I will provide as much as possible material to have it done. What, like, in the form of semi-joke, I was asking you to interview your advisors about the selection rules. Did any of you try? I know that Patricia did not.
I know I didn't.
I haven't seen him since, well, I've seen him, but I haven't.
Wait, what are we interviewing for?
For selection rules.
Oh,
Selection, not like selecting people. Selection rules in spectroscopy.
No.
So you'll do UV spectra, so you did in the labs, and here we did some UV emission spectra of hydrogen, right? So there is a transition energy and intensity, right?
Yeah.
So who is responsible for the intensity? Of which physical process? Chemical process. Which features of the molecule responds whether it will be bright emitter or strong absorber? Band gap defines transition energy, defines frequency or wavelengths. But we have like screens of your palm tops and laser pointer. Who is brighter? Or you have like highlighter pen that may emit like a little bit, but they all have different intensity. If you do experiment, even at the same transition energy, some materials emit better, some emit worse. And same for absorption, right? Like some materials completely absorb light and some let it go through. So who is responsible for the intensity of the spectral light? What do you,
Really
yeah,
should know.
what do you think?
Who is responsible?
What chemical property is responsible for increasing the intensity of the absorbance of the molecule?
The bonds, the bond types.
Or if it is electronic transitions from one electron state to another electron state, then it's like some properties of orbitals. Okay? So which property of orbital? Like there are two orbitals, source and drain, where we start, where we finish. Right? And what should happen between these orbitals for optical transition between them to be intense?
So it would be like going from excited to ground state, right? Because it emits
Yes.
energy.
Mhm.
Like if they're further
Yeah,
apart?
if you're,
the
if
energy
you're
gets
going from an excited state to a ground state, you're using energy, so you're emitting.
Yeah.
Photons.
So is it the distance between, or like the,
Yeah,
The distance between ground.
it gets dropped further.
So the higher the energy state to ground, the more intense it's gonna be.
It wouldn't be completely wrong, but right now we are debating on the language of 19th century physicists who didn't know about quantum theory. There is a dependence on frequency, universal dependence.
It's because of the wave packet propagation.
But if you do have orbitals,
Sure.
let me waste precious time on materials that I'm going to show in just quick. Remind you one of your exercises. If you have something to write this. So, do you remember when you did sine x times sine 2x dx from 0 to L equals to maybe to 5?
Oh. Yes.
So, was it 0 or not 0?
No.
I don't remember. It was something like minus 5/9, but it was non-zero value, and we did it during the. It's like Jon Snow resurrected. Particle in the box. So we have phi1 of x, phi2 of x, dx. So it is matrix element, right? From state 1 to state 2 with operator x. What can you tell about it? Why this task was seeded in your heads 2 months ago? Good question. And if we are not natural scientists, but linguists, which we are not, we can just make connection between the question that I asked at the beginning and the thing that I will So the question was to interview your advisors about selection rules, about intensity of transitions. So returning back to the particle in the box, state number 1, state number 2. And we multiply these two things and integrate and get 0, right? The state orthogonal. But if you place a position parameter between them, it will be non-zero. I am failing to provide background. I will try it later with boring long equations, but no one you have. I know that Patricia potentially can. I was sending her like 200 papers, asking her to read, and some of them with fine font answer this question. And I sent 100 pages long paper half an hour ago, so it described this aspect in all details.
So did you read
Like,
it? Did you read 100 pages? No.
Okay, so if you quickly summarize the. Okay, I will fail to do in time, but we'll get the foundation. What is light?
It's both a wave and a particle.
Yes. If we forget about particles, electromagnetic waves. What are electromagnetic waves? I shouldn't make this stupid faces and focus camera on myself. I should focus on me. So what is electromagnetic wave?
Like radiation.
What is? Why charges move?
Because they're attracted to each other or repulsed.
Good. Thank you. I feel much better. So charges move because they are attracted to other charges. And if you forget about other charges and look locally on the area of space, so other charges from outside that we are not focusing, what they create in this local space that our preferred charge is about to move. What other charges create in the space? Start with letter E. Electric field, right? So charges are moving because of electric field, right?
Yes.
So if you do, and electromagnetic wave is an oscillating electric field that propagates in time, and magnetic as well, but electric is stronger, right? So if it meets a charge on its way, like a molecule with a dipole, right, it will make it the bond to oscillate. It's for vibrational IR spectroscopy. But if it is electronic transitions, then electric field will somehow act on these orbitals, and it must induce transition from lower to higher. So how do electrons in a molecule interact with electromagnetic field?
Electrons in the molecule interact with an electric field.
Yes.
The electron in the presence of an electric field, depending on what the charge of the electric field is.
Electric field doesn't have charge. It's already summarized as the concept of the charge.
Oh, I guess I failed physics too. That's a good
It
question.
would like follow the path of the field.
Melody +1. Thank you for being in class and
They're
supporting the discussion.
someone who actually listened.
So, but molecules are neutral, except very few anions and cations, right? So nothing is circular, but there is a dipole, positive and negative. And like a needle of compass, it will alternate based on the electric field. So if it is vibrational spectroscopy that Patricia is studying right now, then everything is clear. Electric field induces dipole to like contract and expand or to rotate. But if it is electronic states, if we are not, if the time scale is so quick that ions do not have time to move, and we want to see response of electronic orbitals, how do orbitals, electronic orbitals in a molecule interact with electric field? I wasn't right by being impatient. This is a hard question.
You say it one more time.
I'll try. How do electronic orbitals of negatively charged electrons in a molecule interact with incident electric field? They definitely interact because electrons are charged negatively. The question is how. And my success is that you all arrived to silence and intense thinking. When we followed Melody and Patricia on vibrations the first week, we were telling that electric field, which is a vector, and the dipole, which is nothing but center of the positive from positive to negative vector times charge, right? Gives the energy of interaction.
Would they rotate and like align themselves with or against the field?
Yes. Yes, exactly.
Well, because it's
Yeah,
kind of like any bar.
But here is not magnetic, but not
Like 0.1.
That's one friend.
no. Return to the very beginning of the class. You summarized everything what we need in on our meeting number 7 through postulates. So if you need to describe the process, you need an operator, and you need bra and cat. So what if we take? Come here, focus on myself. If you take this operator and plug it into this bra and cat. So we want to find matrix element of interaction between light and matter. So distance between electron and ion is dipole, which is the same as position operator, and electric field, which is of course oscillating, blah blah blah, but it is not. We are not. Everyone except Patricia is not considering it as an operator. So you can put it, put charge and electric field outside of the bracket, charge and electric field outside of the bracket. Then matrix element of initial and final operator disposition operator will give us the transition dipole matrix element. So transition dipole matrix element reflects the strength of interaction between matter and light. The bigger this operator, the more intense will be spectral transition, the more vividly and happily molecule will be excited from ground to excited or returning back and more brighter color will be. So your homework was not a waste of time. This is a foundation of light to matter interaction. Homework number 3, whatever. Good. So if we look on complicated systems like hydrogen atom, it is already quite complicated as you realize, and all other molecules, like rotational, vibrational, one can find spectrum intensity of transition by finding selection rules. Selection rules are basically evaluation of transition dipole matrix element, telling whether pair of orbitals or pair of quantum states will be interacting with electromagnetic radiation. And for some highly symmetric models, those selection rules are quite symmetric. They could allow transitions only between nearest neighbors or some other things. Right now, you do not need to ask your advisors anymore because we discussed it in class. Okay, and as usual goes, 60 slides for 20 minutes. Do not forget this 20 minutes should provide enough information to fill these pages. But did you got selection rules? Intensity of light to matter interaction? Okay, so he got the title of whatever, one of the noble title from the British king, and it was a tradition. Instead of giving Nobel Prize, just promoting to nobility for scientific achievements. So just do scientific achievements, take British citizenship, and get some title. So minerals. The fluoride is a calcium fluoride, right? And if one flashes UV light, it starts flashing back blue or yellow, or depending on the different things. And this Sir Stokes became Nobel, including because he wrote detailed explanation of how he explains fluorescence. So fluorescence comes from the name of the mineral fluoride. Calcium fluoride. There is a very interesting thing. When we were thinking about particle in the box, the absorption emission or hydrogen atom absorption emission happen at the same wavelength, same frequency, right? If we deal with real materials, absorption and emission happen at different frequencies. And this is like, to those of you who probably do real life experiments, it's not a big surprise, but for like, if in all my life I saw only the particle in the box and hydrogen atom, it is a big surprise. How can it be? Like, it's same electronic level, but the energy, what happens, right? And this is a big challenge, and this is what you need to answer in your little surprise quizzes. You're still following.
Yes.
Okay. As a chemist, you probably hate minerals and love small molecules in solution, right?
Yeah.
So some of the molecules under UV light flashback, right? And some of the popular are like fluorescence, because so it is a linguistical sequence: fluoride, fluorescence, and then the molecule that fluoresces is called fluorescein, but the name come from the mineral. Rhodamine, so it's similar to what people have in the eye, the sensor for the light.
Rods.
Rods, but I'm not sure that rods and rhodamine have the same roots.
Yeah.
But I should make a linguistic study, maybe.
I think the spelling is different.
It is.
So RH.
Yeah, there's no H in rods.
So looking this rhodamine, and here are experimental absorption and emission. You see, they are about at a similar frequency, but they have shoulders to a different side. And this is a big surprise to anyone who does this experiment, and it is one of the reasons Stokes got his title. So he did try to explain, although without quantum theory, it was not possible if he just observed it. And here is the absorption and emission of this fluorescein. Of this molecule. So it's for a dye to be able to connect it, it should have conjugated bonds and donor accepted groups, right? Okay. So we are going to reproduce these figures. Right? So in some sense, if you would read my ugly writing easily, this is already an answer to your thing, but you will write there for sure. So what is shown on the board? It's kind of summary. All molecules, just by the having a title of molecule, all molecules, what happens with molecules, do have vibration degrees of freedom, at least one, if it is diagonal. Vibrational degrees of freedom can be quantized, and they are quantum states. And then, even if you consider only one electronic state as ground and second electronic state as excited, each of them have a lot of sublevels, vibrational sublevels, right? So instead of two levels, we all immediately have like 22 or 200, many levels. And instead of finding selection rules and transition dipoles between just initial and final level, we have a lot of levels, right? So we need to take into account. So molecules are much more complicated than atoms because their electronic transition energy modifies when they contract or expand, and the transition selection rules between different vibrational substates to another vibrational substates have also their specific rules. The goal of this last didactic lecture and the goal of your surprise quiz is to convert the rules that we will study in the next 16 minutes into the answer of the problem that is formulated here. And the answer that, did you remember what we looked a couple of slides before? Hey, maybe not.
What about it? Which one?
Absorption and emission spectra that do not coincide,
Yes.
right? So the absorption spectrum goes to blue side if you have energy instead of wavelengths. Emission goes to the red side. And you see these shapes that goes up and down, up and down. This is a way how we will mathematically represent this absorption and emission spectrum. We will focus only on absorption, but one can do the same for emission. The peaks here correspond to transitions between sub-levels, electronic vibrational levels, and they will have different, not only different transition energy, but different selection rules, different intensity, different oscillator strengths, which is a square of transition dipole. And my task in the remaining 15 minutes is to give the answer in form of equation, and your task will be to just plug in numbers into the equation. But the equation will answer how the intensity of spectral transition depends on the frequency. Make sense, or you are completely away?
I think that makes sense.
Following, more or less?
Maybe like in the middle, just slightly up.
Okay, okay. It will be ramping up more and more complicated. Okay. So, what do you see on this in this figure? Good. I'm very happy that a lecture on camels is not wasted.
Energy levels.
Right. So no one selected a project on Markov theory this year, but in previous years many people were selected. So here we are not looking for realistic molecule. We do like artificial molecule that has parameters that are visible and easier to digest. But with a little off scaling of the parameters, it will be observed in the realistic molecules. So this is an absorption spectrum that gets increase of intensity and then decrease of intensity as we go to bluer and bluish. Okay. Those intensity of peaks is what you need to provide by in the next 12 minutes. And here is how you look on the system. So ground electronic state is simple. Let me focus on myself with maximum humbleness. So blue line, blue potential energy surface, and the letter G stands
For ground.
yes, 80+1.
Yeah.
Red potential energy surface and the letter E stands for
Excited.
yes, N+1. And if it would be an atom, not a molecule, we would have just two levels, ground and excited, right? But those are molecules, and energy of each quantum state depends on interatomic distance, right? So it is very normal and very typical that equilibrium bond lengths in the ground and excited are different. There's slightly but different. So if you excite, bond expands or contracts. Now, vibrations, which is elongation and contraction of a bond, can become by Hamiltonian for vibration motion and result the quantum progression of the harmonic oscillator levels. So the thin blue lines are eigenstates of the vibronic state in the ground state, right? If we keep it in electronic ground state but let it shake, it will come to the state. And the red thin lines are, you see, 1 hum, 2 hums, 3 hums are eigenstates of vibrations in the excited state. Okay. Now, if we want to expose this molecule to incident light, then and assume that it is overcooled at 0 Kelvin, so everything is ground, and vibrationally ground state. Then we will have transitions to different electronically excited states. So from blue 1 hum to red 1 hum, from blue 1 hum to red 2 hums, from blue 1 hum to red 3 hums. Are you following?
Yes.
Ask questions. If you lose track, you better restore it. From blue, yes, Patricia, please go ahead.
I'm just trying to round up my head around that the ground state has different eigenstates.
So ground states in the sense of electronic ground state, or electronic degree of freedom. And then we have different eigenstates in respect to vibrational degree of freedom. Okay. So now I hope there will be little, yes, animation. So blue to red, black line, transition energy, something like 0.2 electron volts. This would correspond to this highlighted in red line, right? So transition energy resonance determines the transition energy in the spectrum, but intensity will be a matrix element of position operator between this wave function and this wave function. And the answer is written on the top line of your for in-class quiz. And in the remaining time, I will continue the thing, give the full equation, and ask you to plug in some numbers and fill the table. You'll be able to do it. It's like 2 minutes activity. I need to shut up in 6 minutes and give you 2 minutes to complete the assignment. Okay. So going forward, next transition from science of chemicals, from G0 to E1, right? Highlighted in red. You see it is more intense. And the intensity is G0 E1 matrix element. There should be mu between them, absolute value squared. Going next. G0 E2. It's even more intense. Then G0 E3. And then you see a trend, it becomes less intense. So by some reason, overlaps of this blue and red eigenstates do depend on the transition energy. Something is happening. And then if you go G0 E4, it becomes less intense, G0 E5 even less, and G0 E6 is almost negligible, right? And then we have a profile instead of single narrow line, as I was showing with an experiment here. In hydrogen, we have a band, broad spectral band, as typically is observed for molecules. Next year, I probably should bring like beaker that will flash and show the spectrum, and just better to arrange it in time. So this thing that we need to do. So ground to excited potential energy surfaces instead of harmonic is good. If one wants to be precise, one can do Morse, right? Electromagnetic field is electric and magnetic field that oscillate in space and time. The three dipole, the dipole is what? Dipole is distance between positive and negative vector times electric charge. Interaction is electric field times dipole is minus sign. So if we do, okay, I need to shut up in formats. So here V is interaction between light and matter, and transition dipole is all positions of all electrons and positions of all ions. And we are going from ground to Xi. We are promoted by H bar omega capital, like frequency of light. Now, true science starts. Before the whole class, we were using functions of one or two arguments, but in real life, the amount of arguments is huge. So wave function of a molecule depends on positions of electrons, positions of ions. In Born-Oppenheimer separation that have random fluctuation, Lola did present on the fundamental seminar, one can present them as a product which is not always correct. And we need to find matrix element of the initial wave function of a molecule, which depends on like 100 variables, final wave function of molecule, and the Hamiltonian interaction in between. We are going to, and it is called dipole moment. And the Fermi's golden rule is matrix element of interaction squared defined by multiplied by density of states. Fermi's golden rule gives rate of a process. So if you have rate, if you have this matrix element of interaction squared, it will give rate how quickly it is absorbed or emitted. Therefore, we need square of dipole matrix element. And in the remaining 3 minutes, we will assume that there is only one electron and one interatomic distance. This series situation will be correct if you look for H2 plus. Like it is still a molecule with 2 protons and only one electron. There we need to think that electronic wave function is a superposition of grounded excited with coefficient E, G, and CE. But if we adopt this Born-Oppenheimer approximation, we instead of C, G, and CE, we will need to use vibrational wave functions. So here we assume that we already have the pairs of eigenfunctions. Phi sub m and phi sub n are, I cannot jump so high, are those are electronic. Chi sub m capital, chi n capital are vibration. So those are red and blue things that we were looking at the beginning, right? The transition energy between them. So each of the eigenstates have energy, and by subtracting them, we will have the transition energy. The absorption spectrum originates, formula for absorption spectrum originates from Fermi's golden rule. So F with all these 4 indices is called oscillator strength. It is a transition dipole square. And oscillator strength is what spectroscopists are using. This density of states, we played with delta functions, is a resonance condition with frequency of light and energy difference between initial and final state. Energy difference between initial and final state can be written as energy difference between electronic and energy difference between vibrational levels. So it will be just offset on the x-axis. This is relatively simple, but the F oscillator strength is a big challenge. Okay, I need to shut up in a minute. And here are the most complicated slide. The matrix element that we are looking is these 2 functions and the interaction between. The interaction can be assumed as electronic position times identity operator in respect to nuclear, which means by performing integral over nuclear position, we'll get the overlap of the nuclear wave functions to themselves. And by taking the matrix element of electronic ground inside it, we will get just oscillator strengths of the electronic transition. Okay, so here is the figure that we have, and let me attract your attention once again. We are looking on the blue box here. So this blue box includes overlaps of the blue and red wave functions. And the overlap of blue and red wave functions can be found based on the fact that they're shifted Gaussian, like ground state is shifted Gaussian function. Shifted Gaussian function can be expressed in terms of the excited state eigenstates as a coherent state. And coherent state expressed in a basis does have this expansion. Therefore, if we are going to overlap ground state wave function and excited, we already have the result of this overlap, which are just expansion coefficients of the coherent state in the basis of the ground state of harmonic oscillator. So the alpha is proportional to the shift with the expansion coefficient square root of m omega over 2h bar, which we had as a definition of A-dagger operators. So from quantum factors, which are those intensities, include this coherent state expansion, and those are the numbers that you do need to compute in your table. Third, last column is most important, like after the equation, yes. So if one plugs in the values of mass, frequency, and distance into this conversion factor, one should get about 2, right? Did you? Yes? I hope you did.
Oh.
And then
Yeah.
numbers go from 0, 1, 2, 3, 4, 5, 6, maybe 7. So one plugs in the values of delta E, which will be electronic energy offset plus 0h bar omega, plus 2h bar omega, plus 3h bar omega. So they are offset linearly. And then one just needs to plug in number 2 into that equation. So e to the minus 2 squared times 2 in the power 0 divided by 0. So it will be very small. And then just work on this progression. See where you are. Can you try give numbers by calculator? Tell are they small or big?
You want me to like?
To do just one significant figure.
Okay.
Right? And the power. They will differ by order of magnitude.
Okay.
Like 0.1, 10, 0.01. So I'll show my results, and because we need to rush, and then we can. So when I was plugging number 2, and at the denominator there is a factorial. So e to the minus 4 is the same factor everywhere, and then the rest is we have 4 over 1, 16 over 2, 64 over 4. So we just square function fights with factorial function. At the beginning, the square function wins. after number 4, factorial in the denominator starts winning. Therefore, for the first, it goes up, goes up, goes up, goes up, and then it goes down for next of them. And it's like close to 0, 10, and then 8, 6, and then it declines. And if one takes these numbers that you have computed and plug them into the height of these peaks, one would reproduce the absorption spectrum of the atomic molecule based on Frank-Condon principle. So I did plug this results of your test in the computer, and it is how this image was obtained. Okay, they give like a real number, not.
Oh,
Yeah.
okay. That would save me a lot of time.
Mhm.
Yeah.
Very good.
it is. Yes, it is.
There you go. That's my point. Is that what you were asking for?
Yes, yes.
You got it.
Increase and then decrease. So I will collect, and meeting is done. Congratulations on finishing the didactic